Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. Today, let's talk about a very important topic of this numerical approximation applied to finite elements. And that's regarding the piecewise defined continuous functions. So this is a very, very basis of finite elements. So this is coined by the mathematician Courant. He is the one who started this piecewise approximations. And then he is the one who started in 1940. And this is the very foundation of finite element approximation. So what we mean by this is that until now we talked about so many approximations, including variational formulation and method of weighted residuals. In all those things, if you recall, basically we were talking about, till now we are looking at the approximation in terms of phi hat, say xy or anything. We wrote it as psi naught plus so in this, the important thing which you have to note is that this is a linear summation of several functions, psi naught, as well as many functions psi j, and a summation of this one will form the main approximation phi hat. So depending upon the coefficients, so we have several methods, and we'll find out phi hat. So that means that either not only this one or even the Taylor series or even Fourier terms. So if you look at the terms like even the Taylor series, for example, so a function fx in fact is written as a naught. Of course, there is mild variations on this one. So what is the interval and all that. So in this, what it is that, so whatever be the function which we have here will be approximated by taking a number of terms added together like this one. And not only that, as we add more and more terms, so we are going to have better and better approximation. So let's just look at this one. So if there is some function in some interval, AB, and so we can have several approximations here. For example, if this is approximated by the first term itself, just a naught, then the best approximation would be somewhere here, A0, something like this. So this is a constant term. On the other hand, if you also include one more term, linear, so then a better approximation for linear thing will be like this. So which is A0 plus. So this A0 and this A0 need not be same. And then this is two terms. And also if you go further, so then I'll just use another. So we can also use one more term. If you use one more term, so it may look like this, a parabolic a0 plus a1 plus a2x square. So like this, you can see very well that as the number of terms increase, so our approximation comes closer and closer to the 1. So this looks neat and clean, but then the problem with this one is that every time you add one more term, so the derivatives have to be recalculated. For example, if I have another term here, x squared, then x cubed, then I have to say in the L operator and all that, we have differentiation. So that differentiation need to be done every time you do it. So this is a little time consuming, but that's how it is. Okay. Apart from this, so now what we are proposing, what has been proposed here is that instead of having one interval a to b where the functions are prescribed continuously from end to end, every term is continuously represented here. So instead of that, so let's use piecewise functions. Piecewise continuous functions. So piecewise continuous function here is that we can say the same thing. This is the actual function, let us say, between a and b. And we want to approximate it by, say, a so here we have the piecewise defined functions, such as, let us say, even the constant. So this is several intervals, omega 1, omega 2, omega 3, omega 4. And then we have defined here like this one, for example. So here this is, say, a0, but let's say this is omega 1, omega 2, and omega 3, and several subdomains. And here this is just equal to a0 as defined in 1, and this is a0 itself as defined in 2, and like this. So this is called a piecewise defined functions. So in each part here, this is a continuous function. So this is piecewise defined function in each of these subdomains. Okay. So like this, so we can also have, for example, the next one is piecewise defined linear functions. So that means that we have, maybe I'll draw it again. So let us say now we have piecewise defined like this. So here these are piecewise defined linear functions. This is piecewise defined constant functions. So these are linear functions. So these are linear functions. So in each subdomain, so it is given by, so in each domain, for example, here this is a0 plus a1x, but then these coefficients are only a0 and a1, they only belong to this domain omega 1, and like this. So we have here a0 to the fourth domain and a1 x to the power. So you can see that so you can see very clearly that in each domain it is a linear function, but the two coefficients which appear here are different in each subdomain. So like this, you can also extend this one further. You can also increase the piecewise defined functions degree to quadratic. So for example, so I'll show it. So if it is quadratic, you know that it's like this. So it becomes. So one thing what you observe here is that though these are piecewise defined, here also the approximation which we are assuming is getting closer and closer to the exact value by choosing more number of subdomains, right? So in each subdomain, it is defined by 2 coefficients, or it can even be defined by 3 coefficients. So what important thing here is that, so if this is the basic part of the finite elements. So what is the advantage here? One thing is that it's very clear that by taking more number of subdomains, you can come closer to the exact value. That's number one. Number two is that compared to this original approximation where we have higher degree terms, here I can have 4 here. I can also have 5 subdivisions. In each subdivision, it is linear only. So basically, the nature of approximation in each subdomain remains same. It is defined by a constant a0 and a1 belong to that subdomain. So even in this case now, so that means that when you apply the procedure method of weighted residuals to this one, like L5 hat, or even weighted residuals, so when you evaluate this one, so you have to do this phi hat, and this subdomain here, this domain here can be subdivided into this, like this one. Okay, so it has to be subdivided into a number of integrals over domain 1 and 2 and 3, and here anything like 5 and so on, as you go on increasing the number of subdomains. So the advantage here, you can see that here, is that when you evaluate phi hat here, this phi hat here is belonging to 1, and here this phi hat belongs to the domain 2, and here this one belongs to 5. You understand here? I didn't put the L here. That means that this phi hat, what you have to use in this integral, has to belong to phi hat 1 and phi hat 2 and so on. So when you look at the phi hat here, is that we have to use, if you want to use the phi hat 1, what you have to use expression is this one, a01 plus a1 of 1 times x. And then similarly here, when you use 2, so then you have to use a02 plus a12 times x. So like this one. So the nature of the integral remains same. The type of integral which you do here is the differentiation followed by a wi and then integration. So this is all same. It's all systematic and you can do it. Really, you can now imagine that this whole thing can be computerized, and put it in a very systematic manner. Okay, so that is the beauty of this piecewise defined continuous functions, right? So the nature of phi hat will remain same in each subdomain, and the accuracy of this phi hat in an overall sense will increase as the number of subdomains increase. So here the subdomains are called elements from the finite element point of view, and of course there's another term also that comes into the picture is the node. So node is nothing but the point at which the elements are connected. So these subdomains are called elements, and points at which elements are interconnected. So these are called the nodes. So this is the general terminology. Okay, so it looks theoretically, so it's very appealing, and so this is the procedure. But what is that which we have to take into account here? So we fully took this omega as omega 1 plus omega 2 plus omega 5 will constitute the thing. But if you look at this one, so our integral has to be this one. So L has a phi hat. In the phi hat, in the sense that what is phi hat here? So if I recall, what is phi hat? Phi hat, so this is phi hat over the whole domain, which is subdivided. So that means that our phi hat here, if I draw it in the blue, is this. This followed by this, followed by this, followed by this. So if you take the linear approximation here, is that in each domain it's linear, but then what happens at the interconnected point, that's the node. If you look at carefully at the node point, at the nodal point, so there is certain amount of discontinuity is there. So how is it going to affect us? At each node you can see the disconnected, because as such this integration has to be carried over the whole domain. So that means that over whole domain. So we are doing it omega 1 and omega 2. What about the interconnecting point? What happens there? So is this allowed? So that we have to answer. So let us look at that. So those are very important considerations. So let's look at that. In what way it is going to affect. So in this evaluation, so I'm writing it here again. In this evaluation of this, it may be this L, or it may even be B, or it may be any other integral. It's very much you have an integrand and which is integrated over the domain omega. So phi hat is piecewise defined. So that means that phi hat is equal to phi hat 1 in omega 1 and equal to phi hat 2 in omega 2 and so on. So what happens, so that is fine as long as you do the integration within the element, but at the element boundaries, what is that going to happen? Is it going to be a disaster? So as such what it is that from the functional analysis, so whenever you do the integration of any function like here, then the integrand has to be integrand for integration as such, the integrand has to be continuous and well defined and single valued. So this is the one which is going to trouble us. So as such, if this has to be integrated, so the whole integrand, okay, whole integrand here has to be continuous. So continuous in the sense that it has to be single valued. So but however, here we have a discontinuity here. So let us just look at this one for a while. So that means that the function has to be continuous. So if f or phi hat is here, if L is, say, if this is the rth derivative occurring in integrand, that means that this phi hat has to be this phi hat here, then the has to be continuous. So in the integrand, it is just not the function, but it is the derivative that is appearing there. So that means that the rth derivative has to be continuous. So this is, so within the element domain, of course, they are continuous functions. So the derivative is no problem. Only the problem is coming at the element connection, that's at the nodes, at the element boundaries. So let's so such thing, if you have rth derivative which is continuous, so then that is called the CR continuous function. So let us just see what is continuity order. So for example, if you just look at this one, so look at this one. Just I'm drawing two domains, two elements. So 1, 2, 3. So let us say, so this is phi hat defined as two linear functions like this one. So if phi hat is like this one, piecewise linear, and then it is connected like this one. So this kind of thing, so if you take a derivative of this one, then if you look at the derivative, so what happens here? So the first derivative is like this, and the second derivative is like this one. So this is the derivative here. So if you look at this one, so what kind of function which we call this one? So here the function is continuous, right? But its derivative is not continuous. So derivative has a discontinuity. There is a discontinuity here. In the sense that suddenly from this value to another value, it is jumping. It is jumping to another value. So if you look at the another type of function here, let's look at another type of function. look at this type of function at defined. So we have two domains, omega 1, x1 to x2, and omega 2. So this kind of function, if you look at that, so there is one kind of parabola here and another kind of parabola here, second degree. And so if you look at d phi by dx and d square phi by dx square, so d phi by dx is linear in this and continues to be here, and the linearity changes here because the slope suddenly has started increasing here. Okay, but however it is the same at this point. But then we have a d square phi by dx square. If you take a second derivative, then it looks like this one. So here compared to this one, here the phi hat is good enough. The first derivative is fine, but only the second derivative is having a discontinuity. So this kind of function is called, so this is C1 continuous function. Because there is a second derivative existing. First derivative is continuous, but however the second derivative. So whereas the one which we talked about earlier was a C0 continuous. So this continuity which we are talking at the node 2, but within the element it is more, definitely is far more continuous, in the sense that if you want to take a second derivative or even first derivative, second derivative, it's fine here. You can also have first derivative, second derivative, here it's fine, or even third derivative. But however, what happens is that at the node here, at the interelement point, so that's where the discontinuities will take place. So the question now is that, coming back to this discussion here, so for example, if L, so let us say if L is having a first derivative like this one, so then what you can use as such is that if it is having a first derivative, so the first derivative here has to be continuous. So if you look at these kind of approximations, so then the one here d phi by dx is having a discontinuity. So as such, it is not acceptable. Whereas here, this d phi by dx is continuous. So this seems to be, so seems that we need C1 continuous function. Okay, C1 continuous function. Okay, so that means that we need these kind of functions where the d phi by dx is definitely single valued and continuous. The next thing is that, according to the Courant and the development of finite element analysis, is that, so the requirement or the requirement of continuity has been relaxed. So the requirement of continuity. So what essentially, so for example here, if we have a d phi by dx here, and then if you want to integrate this part or the domain here, so there are, it's d phi by dx and phi and d phi by dx square and so on. So in all these things, if you have this, so what is the kind of requirement which we need? So that is important, a very important part of finite element analysis, and that's what we are going to discuss in our next class. Bye.